So good morning. Welcome to Krishna's classroom. We continue from where we left in the last class. So we were doing the abstract formulation of the quotient spaces, and we more or less finished with it. And then we said that we were exploring what is the dimension of the quotient space. So the preliminaries are V is a vector space of dimension n over a field F. M is a m-dimensional, n-dimensional, m-dimensional subspace of V where 0 less than m less than k. That is, m is a proper the other two cases 0 and n are trivial and goes in the same way, but you don't get anything special. So we don't want to. Probably I will towards the end I will say one line about it. This is the scenario. So we had V by m concept, and we found that V by m, which consists of is a vector space. With the identification that x is related to y belonging to that. With this identification. And we have seen that this is an equivalence relation, therefore this classifies it, etc. And we have addition and multiplication defined. So we denote by x bracket, and then we have x plus y defined by x plus y. It is well defined. Then c times what? The other way around. C belonging to, and of course x belonging to. Now with these definitions, V by m is a vector space. This is the addition and scalar multiplication. We have shown that this is properly defined. That is defined without any ambiguity and makes a vector space. And we have also seen a model in R2 how things work. And they given a subspace, proper subspace of R2, which is a line passing through the origin. The elements of the vector space V by m are the lines parallel to it which is a sort of disjoint union, or whose disjoint union gives the whole space. So all those things have been looked into. Having proved that this is a vector space, we ask the question now: what is the dimension of? So this is the question. I have made some remarks about this question in the beginning. Now we have arrived at certain conclusions, and our speculation is that it is something like n minus. Okay, so we will investigate. How do you work on this? Now we actually construct a basis if possible. Construct a basis. So we shall construct a basis for B by M. Okay? But how do you go about doing it? From our experience, we have seen that we will choose a complementary subspace for M, where of course what we mean by a complementary subspace is that, see, N is a complementary of M in B one, two, so you can show that actually M plus N for any given subspaces M and N of P, M plus N is a subspace of P, maybe the whole of P. Okay. And M intersection N may be the zero element or may not be. It is also anyway a subspace of P. So if M plus N is equal to B and M intersection N consists of only the zero vector, then we say N is a subspace complementary to M in fact, what we observe is that there are several such subspaces that we can choose. It's not just unique except in the extreme cases. Except in the extreme cases, it is unique. It is not unique. That's the point. So, M proper implies there exists a multitude of choice something as we have seen in R2, we have this is N, then any vector parallel to that would be N. Okay, the only thing is that M and N cannot be identical. Okay, so any line, every line, so this could be an N, this could also be an N, this could also be an N. So N1, N2, all these are complementary subspaces. Now that is the point. Right. But one thing from this example that you observe is that here n, n1, n2 all have the same dimension, although these subspaces are different. And the dimension is given by, since M has dimension 1, vector space V is R2, therefore the dimension of, it turns out that the dimension of N is equal to 2 minus 1, which is equal to 1. So in general, in the vector space V, one can show that the complementary subspace has dimension n. In fact, see, there is a nice theorem. It's a general theorem. Now suppose the second condition is satisfied, then this is going to be 0. So in that case, if 2 holds, then dimension of if 1 holds, then dimension of n plus n equal to n, which implies that's a proof of this. So what we are going to prove is that the dimension of V by M is equal to, so theorem, n minus n. So we construct a basis for V by M consisting of n minus of M vectors. And from this previous result we have already seen that it is equal to dimension of n. Therefore, you see n minus whenever n is complementary subspace of Therefore, it suggests a way. Suppose we know a basis for n, then is it possible to compute or concoct a basis for v by n? Okay. So that appears to be a strategy if our theorem is true. So let us explore this. So first thing is that we start with a basis for m. Now, one can expand this to a basis for v by adjoining n minus m vectors minus m vectors. So how do we do this? We shall do this as follows. And we shall take span of n. Okay, and you see that this is linearly independent. Therefore, the dimension of n is equal to dimension of n equal to okay. So this is the arc. Or you can also say that you start with m, choose a complementary subspace n, and then take a basis for m, take a basis for n, put them together, they together make a basis for v. That is quite easy to prove. Okay, so that is one way of doing it. The other one is simply start with the basis and then you construct a basis for, or you take a set that spans v adjoined to this and then slowly start building up a basis for from that. That means you have to choose a linearly independent set. So that's not physical. Okay. So either way you can do it. Maybe I will show how you do this. So given M, then B, choose a complementary subspace. Then B equal to and M intersection and 0. Now choose. So x1 for is the basis for M. Now you know that the dimension of equal to n minus. Let be a basis for n. Then how to prove this? You see that B equal to M plus N implies any vector x belonging to B can be written as x is equal to y plus z x is equal to y plus. Now y belongs to M and z belongs to N. Therefore y is a linear combination of sigma I equal to 1 to M Ci xi. So also z equal to sigma I equal to 1 to j equal to Ci xi. That means this is equal to Cm plus 1, Xm plus 1, etc. Therefore, now we prove that this is also linearly independent. So we now show that sufficient to show that so let us say, so you see that sigma I equal to 1 to n ci xi equal to sigma I equal to 1 to n ci xi plus sigma j equal to 1 to n plus 1 to n Cj this is equal to this implies sigma I equal to 1 to m ci xi equal to 0 and sigma j equal to m plus 1 to n cj xj equal to 0. Why? Because you see that this is certainly a vector in M. This is a vector in N. Okay? Since the sum is equal to 0, you see that these vectors are separately in both M and N. Because what you end up with, you see like this. We have sigma I equal to 1 to m minus of sigma and this is belongs to M. This belongs to M. Therefore, both these belong to M intersection N. Okay? So both and so also sigma j equal to m plus 1 to n cj xj belongs to, but being a complementary subspace, n being a complementary subspace, which implies equal to 0. plus 1 to n equal to 0. And x1, x2, etc. xm is a basis for m. M plus 1, xm plus 2, etc. xn is a basis for n. Therefore, they are linearly independent, and hence this implies I equal to 0 for n. Okay. So that actually tells you that this is a basis for, that is x1, x2, etc. xn. So we can construct a basis. So this also gives a construction. You choose a complementary subspace n, choose a basis for n, choose a basis for m, put them together, you get a basis for v. Okay. So having done that, what you do now? Now what one does is the following. We take a lead from our example. So we have got now these are the cosets. These are the cosets. So if you have any, if you choose n. Now you see that n cuts each one of these lines at a unique point. Okay. So what you do? You choose. See, you choose a basis. So what you do is here you choose x, and then every other element is a scalar multiple of that in the case of R2, but not necessarily in the general scenario, because even in R3 you can see this. Choose a line, then you see that the complementary subspace is a plane cutting it or passing through 0, 0, 0 in R3, and then you see that the complementary subspace is a two-dimensional subspace. So what you do is you choose a vector, choose a basis for n, which will be two linearly independent vectors in the plane. Okay. Through each one of these vectors, they generate one line parallel to the given line. So corresponding to each one of these elements, there is a line parallel to the given line. Therefore, the method would be to choose those cosets of m. So let us consider the cosets. Denoted by what? Xj. Now what we have is that xm plus 1 xn. This set is a linearly independent set. Forms a basis for. What do we do? We ask this question. Is the basis for we expect this to be true because from our experience of working on examples, it's really true. So we shall do. So what we need, we have to prove that this is a basis for V by M, or every element of V by M can be written as a linear combination of xm plus 1, xm plus 2, etc. These elements, and then they form a linearly independent set. So first let us explore that this is a linearly independent set. Yes. So we prove that. We shall prove that. So first what? Do they form a linear? So the first question is okay. So we look at this relation. Let Cm plus 1, these are all generic constants, not the same C that we are using. These are generic constants. Different places they take different meaning. Equal to 0, which is equal to m. Then what do we have? What do we want to prove? We want to prove that Cm plus 1 equal to 0, Cm plus 2 equal to 0, etc. Cm equal to 0. Then we want to prove that. So what is the meaning of this? The meaning of this is this. Then we have the quotient generated by Cm plus 1 which is the right hand side of, which is the left hand side of the above relation. This is equal to m. What does this mean? This means the following, that is, xn belongs to M. That's the meaning of it. That's quite easy to see, because this, a typical element of this class is this plus a vector in M. Okay? And then that is equal to some vector in M. Therefore, you see that this is equal to the, okay, so this is what we have. Sigma j equal to m plus 1 n cj xj plus some y equal to z. That's it. Which implies, see, this is a vector in M. This means C M plus 1 x M plus 1 Cn xn equal to some C1 x1 plus Cmxn. That means this is a vector in M, and that vector can be written as a linear combination of x1, x2, etc. xn. That's what I say. What does this mean? So this implies a linear combination of C1 x1 plus etc. Cm xn minus zero. What does this mean? This means that a linear combination of x1, x2, etc. xn is 0, and x1, x2, etc. xn forms a basis for B. Therefore, this implies in particular Cm plus 1 equal to 0, Cn equal to 0. That is therefore this is linearly independent. That you have to address is, does it span and V by M. Let us explore this. Let then x is equal to, then what you have is that x plus m anyway. So this is a typical number. See, therefore x is in B. X belongs to B implies there exists constants B1, B2, etc. Bn such that x is equal to B1 x1 plus Bm xm Bm plus 1 Therefore, what you have is that equal to excellent. Therefore, you see that any x belonging to B is of this form. Okay. Therefore, x plus V, x plus n is equal to now what we have to check possibly is this. Okay. So before I just assert this, okay, before I assert this, therefore my claim is this. This is equal to This is what make it. So what we have to check is the following. See, what one has to check is the following. Suppose then what you have is this. Then what you have is x minus x prime belongs to here. Okay. Right? X minus x prime belongs to here. Then x prime is equal to x prime. That is x minus x prime is an element of n. So x, that is equal to x plus some y. Y belongs to therefore, now we look at the representation of x prime. Okay, so x prime is equal to what is x? The x is equal to b1 some y is equal to say c1 x1 plus etc. So cm. Therefore, this is equal to what? This is equal to dm plus 1 x1 plus c1 plus d1 x1 plus etc. c n plus right. Therefore, the coefficients of x1, x2, etc., xn in the representation of x prime is the same as the representation that you have in x. Therefore, the coefficients of x a plus 1 remains the same. Whenever x minus x prime equal to. This implies the following. Mod x prime is also equal to dm plus 1 So whenever x prime equal to the bracket x prime equal to the bracket x, I think they have the same representation. Okay. Therefore, which implies that the representation of x, whether you use x or x prime to write it up, you always get the same representation, which implies so we start with an element in V by M, then we write it as, find out the representation of bracket x in terms of dm plus 1 etc. dn. What we have shown is that suppose you are also choose an x prime in V with the property that bracket x is equal to bracket x prime, then you end up with the same representation. So there is no ambiguity at all. So this in turn implies where have we got this x1, xn plus 1, xn plus 2, etc. xn? It came from a complementary subspace. So what have we proved? So together we have proved that is linearly independent and spans M and is therefore the basis for so we have done more than what is required. We have shown that V by M has therefore dimension of V by M equal to n minus M, which is also equal to dimension of okay. So that completes the right. Therefore, we have constructed a basis for V by M. You have seen that there are Several choice of a basis for V by M. Whenever this is a non-trivial space. Okay. Now we claim that so the next result that we have is that V by M is isomorphic to V by M is isomorphic to M, where M plus N equal to V and that is their excess. V by M is isomorphic to every complementary very complementary subspace of that. So we shall do this. We shall actually construct that isomorphism. So let a lesson like this, such that we have already seen that. A basis B basis of N determines a basis for that is y1, y2 should have y n, then now we define a mapping. So D by M is isomorphic to. So define y of xi, so equal to y, where y1, y2, etc. yn minus n is a basis for I equal to for I equal to y1, y2, etc. yn minus 1 is a basis for n. Now extend this. So this is on a basis. Now, if y belongs to b by n, then y equal to some c1 y1 cn minus n minus n y n minus n plus an element in where x belongs to then we have already seen that these coefficients are uniquely determined. Okay, right? Right? That's what we have worked out previously. Prime, where x prime belongs to. So this, if this identification is there, so irrespective of what represents this one, you always end up with the same coefficients for y1, y2, etc., yn minus n. This is what we have proved, or you can directly verify this. That is this. Okay. So irrespective of we get self, and therefore extends the definition of y to all elements of y of two this we have already defined, and this is equal to C1y1 plus which belongs to what is that, n. So that's the definition of phi. Phi has been defined on the basis crafted out from a basis form n in this way, and from then on we extend it to all elements through linearly. So by linearity we have extended it. Now verify that. Y of it's something y of this is routine. Okay. Right? So these are the things to be, right? So phi is linear. This will give you that. This is the definition of phi. Why do you have? So you have phi y, phi z defined, and then add that, and it's just a routine manipulation that you have to do, working with the basis y1, y2, etc. yn for y1, y2, etc. yn minus 1 for. So I leave the computation here. So So phi is linear. So phi is linear. Okay. Once again, thank you very much.